Section 13.6, directional derivatives and the gradient. So just kind of informally, the directional derivative is going to give us the slope at any point on a surface. And the direction of the directional derivative, let me just write this down for you. The direction of the directional derivative is going to be a unit vector of the form u equal to cosine theta in the I direction plus sine theta in the j direction, where theta is the angle the vector makes with the positive x-axis. The angle the vector makes with the positive x-axis. Okay, so to find this directional derivative, we have got a lovely definition. So let's write that down. So definition of the directional derivative. There we go. Okay, we're going to let f be a function of two variables. Be a function of two variables, x and y. Okay. And we're going to let u, as I said just above, be cosine theta in the I direction plus sine theta in the j direction, where theta is that angle with the positive x-axis, and it's a unit vector. Then the directional derivative of f in the direction of u. I'll write that down. The directional derivative of f in the direction of u, seems a little redundant, doesn't it, is denoted d sub u f, so duff, which is given by d sub u f of xy is equal to the limit as t goes to 0 of f of x plus t cosine theta, comma, y plus t sine theta, minus f of xy all over t. Looks familiar, doesn't it? Absolutely. So we have this little incremental change along with u, right, parameterized by t. So that's our incremental change. Then we subtract the original point, divide by t, take that limit. What have we got? A derivative. So this is the directional derivative because our change is going in the direction of our unit vector u. Put a box around this guy. There. Oh, and this, of course, assumes that this limit exists. If the limit doesn't exist, then clearly the directional derivative does not exist there. Now, since we have this whole derivative thing going on, of course, there is an easier way to find this. We don't have to use the definition every single time. So we have a theorem that says that given f and u, that duff, it's just fun to say, duff is equal to the partial derivative of x, the partial derivative of f with respect to x times cosine theta, plus the partial derivative of f with respect to y, sine theta. Okay, and that's for the same u and f as above. So let's go ahead and do an example. Okay, so let's find the directional derivative for f of xy equal to 4 minus x squared minus 1/4 y squared at the point 1, 2 in the direction of u equal to cosine of pi over 3 in the I direction plus sine of pi over 3 in the j direction. All right, so we know that duff is equal to fx cosine of theta plus fy sine of theta. So that's going to be equal to, fx is negative 2x times cosine of pi over 3 plus fy is negative 1/2 y times sine of pi over 3. And we're looking for this at the point 1, 2, so we can plug those values in for x and y. We get negative 2 times cosine of pi over 3 is 1/2, yes, minus 1/2 times 2 times sine of pi over 3 is root 3 over 2. So that's going to be negative 1 minus root 3 over 2. So there it is. There is the slope of the surface at this point in the direction of u, which is cosine pi over 3i plus sine pi over 3j. Okay, so that is the most analogous thing we have to slope in 2 dimensions here. It's just our slope given a certain direction, in a certain direction. Okay, so now let's talk about something called the gradient, which is essentially a directional derivative in a specific direction. The direction of the gradient is going to be the maximum increase. It's the direction of maximum increase in the z value. So whenever we have the gradient, we're talking about that. If we want to know, hey, what's the directional derivative in the maximum, what's the maximum possible directional derivative? What's the greatest possible increase from a given point? Well, it's going to be in the direction of the gradient. Okay, so now I feel like I sufficiently muddled that explanation. Let's go ahead and just write down what the gradient, the definition of the gradient. Okay, so the gradient. All right, so we're going to let z be a function of f of x and y. So we have z equal to f of xy, okay, such that the partials with respect to x and y both exist. Okey-doke. All right, then the gradient of f, then the gradient of f, which is denoted by grad of f of xy, or more commonly the upside down triangle known as del, we just read it gradient, of f of xy, is the vector, okay, gradient of f of xy is equal to, okay, here it is, the partial derivative of, with respect to x in the I direction plus the partial derivative with respect to y in the I direction. That is the gradient. And that gradient gives us the direction of maximum increase from any given point. Okay? So we'll outline that in just a moment when we talk about the properties of the gradient. For now, let's just go ahead and find the gradient of a function. So here's our example. Suppose I have f of xy. F of xy is equal to y ln of x plus xy squared. Okay, then the gradient of f of xy is equal to partial derivative with respect to x, so that's y over x plus y squared in the I direction, plus partial derivative with respect to y is ln of x plus 2xy in the j direction. There it is. There's our gradient. That is the vector that shows us the direction of maximum increase. Now, if I want to know the gradient at a specific point, so what is the gradient of f of xy at the point, say 1, 2 again, then I just plug in those values. So that's going to be equal to 2 plus 4, so that's 6 in the I direction. I don't really need square brackets for this, do I? 6 in the I direction, plus ln of 1 is 0, 2 times 1 times 2 is 4. So 6i plus 4j, or in component form, just 6, 4. The vector 6, 4. So either of those are acceptable. All right. Okay, so as I said, because this is a vector, we can write this, we can write the directional derivative of f using the gradient, right? Okay, so we can write our directional derivative as being equal to the partial derivative with respect to x in the I direction plus the partial derivative with respect to y in the j direction. Okay, dotted with our vector u, so that's going to be cosine of theta in the I direction plus sine of theta in the j direction. Okay, in other words, that is going to be the gradient of f of xy dotted with the vector u. Okay, so that's another form of duff. So let's see an example where we actually find a directional derivative using the gradient. Okay, so example. Let's find the directional derivative of f of xy equal to 3x squared minus 2y squared at the point negative 3/4 0 in the direction from P, which is the point negative 3/4 0, to Q, which is the point 0, 1. Okay, well, we need to know what our directional, our direction is, our unit vector that's giving us our direction. So U is going to be equal to the vector PQ divided by its own magnitude so that we normalize it, right? We get a vector of length 1. So PQ is going to be, let's see, 0 minus negative 3/4 is positive 3/4. 1 minus 0 is 1, divided by that magnitude. So that magnitude is the square root of 3/4 squared plus 1 squared. So that is 3/4 1 divided by, so that's going to be 9/16 plus 1, which is going to be 25/16. The square root of 25/16 is going to be 5/4. So this is going to be 4/5 times 3/4, comma 1, which gives us 3/5, comma 4/5. So that's U. That is our U. Circle that so I don't lose it. Okay, and we know that our directional derivative is equal to the gradient of fxy dotted with u. Okay, so I know what both of these are, or I can figure them out anyway. So then our directional derivative is equal to, okay, so the the gradient of f is going to be, let's see here, 6x in the I direction minus 4y in the j direction. So those are the partials with respect to x and y, respectively. And we are going to take that vector and dot it with the vector 3/5 in the I direction plus 4/5 in the j direction. So remember the dot product, we multiply corresponding components and then add that up. So this is going to be equal to 6x times 3/5 plus negative 4y times 4/5. So that's going to be 18x over 5 minus 16y over 5. And we were looking for this at a specific point. That point was negative 3/4 0. Okay, so that's going to be 18 times negative 3/4 over 5 minus 0. Plug in a 0 for y. So then that's going to give us, let's see, 4 and 18 will reduce a little bit, giving us negative 27 over 2 times 5 is 10. So our directional derivative in the direction of maximum increase is given by negative 27 over 10. So that is the slope that's going to take us to, back that train up, I'm so sorry. That is the slope in the direction of PQ. So that's going to be the slope of the surface in that direction. The direction of maximum increase would be given by just the gradient. Okay, so that's a good segue into the properties of the gradient. All right, so we're going to let f be differentiable at the point xy. Okay, then number 1, the gradient, if the gradient of f of xy is equal to the 0 vector, then the directional derivative of f at xy is equal to 0 for all vectors u. Makes sense since we're dotting with, since the def is equal to the gradient vector dotted with u, it makes sense because if you dot something with the 0 vector, you get 0 vector. Okay? 2, the direction of maximum increase of f, the direction of the max increase of f is given by the gradient. The gradient of f of xy, and the maximum value of def is the magnitude of the gradient. Max value of the directional derivative is equal to the magnitude of the gradient. And finally, the direction of minimum increase is exactly the opposite direction. So minimum increase meaning maximum decrease. Minimum increase is going to be the opposite gradient, the opposite of the gradient. Okay, and then the minimum value of the directional derivative is going to be the opposite of the magnitude. So that's going to be the opposite of the magnitude of the gradient. All right, so one last thought on the gradient. Because the gradient shows the direction of maximum increase, it is always going to be perpendicular to a level curve or to a contour line. Okay, so theorem, the gradient, let me back up, we'll just spell this whole thing out. If f is differentiable at a point x naught, y naught, differentiable at x naught, y naught, and the gradient of f of x naught, y naught is not equal to the 0 vector, then the gradient of f at x naught, y naught is normal, i.e. perpendicular, to the level curve, level curve or contour line passing through that point. There we go. So because contour lines are always running around where it's dead even, like where the z is the same, so where z is not changing, where that height is not changing, or that f of xy is not changing, then it makes sense that that would lie perpendicular to the maximum increase, right? So we're just going as far off of that as possible. So it's going to lie perpendicular to the contour lines. Okay, so all of these properties that we've looked at so far for the gradient have been for functions of 2 variables. Every last one of them for the directional derivative and the gradient are going to extend naturally into functions of 3 variables. So those are all going to be the same, just, adding on that third component. So everything is the same for that. So hopefully no surprises there. But as always, if you have any questions, please do let me know.